Hello and welcome everyone to the channel. I'm your host Stefan Burns, and today I am joined by Randall Carlson, known by many, beloved by even more. And first question, right out of the gate, Randall. I mean, people have been following your work for a very long time. Younger Dryas impact, comet impacts, and massive floods and water discharge across the United States, and many other things. You also go into sacred geometry and spiritual concepts and a ton of stuff. What has been like a research interest of yours over the past few months, or even if it's been a longer time frame, past like couple of years? Like, what's really kind of captivated your interest recently, or like has a hold on you right now?
I would say trying to come up with a holistic model of these global change events. And so this recent trip to the Azores was kind of to confirm that there were massive events along the mid-Atlantic ridge during the deglaciation phase of the last ice age because of the very rapid filling of the North Atlantic with glacial meltwater. So, you know, I've been pretty much obsessed with these paleohydraulic events of that same period. And so I've spent many hours out in the field looking at these landscapes that have been carved by megaflows of meltwater, or megaflows of ultimately waters that were originated from rainfall. So anyways, the idea, you've got these huge floods that have swept over the land, left their imprint, have dumped into the global oceans, have caused a rapid rise of sea level, and that actually is such the weight. I calculated at one point, I don't remember exactly what it was, but it was well over several billion, quadrillion tons, I believe. Definitely up into quadrillions of tons of meltwater. Now, most of that, some of it went into the Pacific. The Cordilleran ice sheet that was on the western side of Canada over the Canadian Rockies and down into northern Washington, that all drained into the Pacific. But the most of it, like the entire Laurentide ice sheet, which was the biggest one, about the size of the Antarctic ice sheet, that all flowed into, ultimately ended up into the Atlantic. Some of it, a lot of it was discharged down the Mississippi River. So there's a gigantic sediment fan. And in fact, New Orleans is built on the sediment fan that was built in turn by copious amounts of sediment-laden meltwater coming down the Mississippi and draining into the Gulf of Mexico, which, of course, then ultimately became part of the Atlantic water. The northern sector of the Laurentide ice sheet either drained directly into the North Atlantic, mostly via the St. Lawrence Seaway, but a lot of it drained into the Arctic first, drained north, and left as its calling card in the aftermath what is presently a scabland complex in an overfit valley situation up in the Mackenzie, where it discharges into the Arctic. So to get back to your question, looking at the effects of this melting, then what is the response to the ocean to this huge influx of mass? Because we know there's a response from the continent. I mean, because right up there around Hudson Bay, you've got almost a 2,000-foot isostatic rebound after the removal, right? So since the geoid is always trying to maintain equilibrium, it follows that if one place is going up, someplace else is going to be going down. And that place, the obvious place for that, is along the mid-Atlantic ridge. And there is a triple plate junction right there due west of the Straits of Gibraltar, flanking, or I should say the right there where the Azores microcontinent is it's called, which is a plateau. And there's empirical evidence that would suggest that landmass has subsided substantially since the late glacial maximum. So I was there mainly just to kind of get the feel of what the place was like and to see if there was anything that caught my eye. There was a few things, that I brought back from there. I was looking at the geology because Plato describes that the infrastructure of the city of Atlantis was built with the rock that was quarried when they created this massive canal system. And then that rock, he doesn't, of course, give the petrology of them, but he just describes them as red, black, and white. And so they quarried the rocks and then built this infrastructure with these red, and then they sheathed a lot of it in whatever this is, orichalcum. And I don't know what orichalcum is. I don't claim to know. I think there's some people out there who are saying that they know what it is. I'm not sure.
They called it the specific like Latin or Greek, I guess it would be Greek name. They called it orichalcum, but we don't know what it is. This is what they called it.
Yeah, that's what Plato called it.
Okay.
And that doesn't specify really what it is. But I know there are people that have researched that particular detail deeper than I have. So there may be some scholarship out there where they've come up with a rational conclusion of what it is. I know there's been speculation that it could have been some kind of a material that had probably had. I think one of the conclusions was that it probably had copper, was some kind of an alloy of copper. What that could be, whether it was bronze, I don't know, but I would think that whatever in the translations of Plato's dialogues that I've seen, it just says orichalcum, so it doesn't really give an explanation. It doesn't say brass, it doesn't say bronze, it doesn't say copper. So that's kind of an open question. But so the plateau itself, if you pull up Google Earth, I should have actually pulled it up.
Yeah, so I'll do that right now. And before I do that, I also just want to quickly show this sea level map from the Ice Age, because I also just looking at this is like, I think we underestimate really how different the world looked that long ago unless you look into it. And then I'm getting a sense of what you're talking about with the Azores and the subsidence, because the sea level change doesn't look any different for them with this map here, but it doesn't take that into account. Right. So if that was taken into account, this would be a significant plateau, and we'll see that on Google Maps in a second. But that's what this shows for the Azores. Yeah. Mm-hmm. But here's the Laurentide ice sheet, which is just a massive amount of mass, as you described. And what I found interesting too, looking at this, is this totally changes the ocean circulation dynamics, the land bridge.
Absolutely. Oh, absolutely it does. In fact, one of the things that happened is once the sea level rose over the land bridge, then you had the warm Pacific waters accessing the Arctic Ocean. And that completely changed, it, because there you can see it's almost isolated from the rest of the global ocean. The Arctic is there, except you've got that one passage there between the Greenland ice sheet and the Fennoscandinavian. No, not that one. That one, yeah, right there. Now you'll notice that right now, it's open between Greenland and the Laurentide, and there you've got an ice bridge connecting Greenland to the Laurentide over there to the left. Yeah, right in there. Yeah, right in there. So you can't see, but there's that little skinny tongue of ice that goes up to the Arctic Ocean, go up and then to the left, right there. It looks like, that guy right there that's coming out, that's where the Mackenzie River discharged into the Arctic. And it's cut a valley. And so what this is doing there, it's showing that valley probably pre-existing, or, that little tongue of ice there is occupying what is now a big, gaping, colossal valley that has scabland and megaflood carved features in it.
Anything else you want to check out this map? I mean, before we get to
let's go back to over Europe. So there you can see the scale of the ice, and look at where England and Scotland would be. Yeah, right there. So, and then you've got it's not separated. It's part of the Eurasian continental landmass, and what's the plain there called? You're on it right now, which is now part of the North Sea. All of that is under the North Sea right now. And get this, the floor of the North Sea has massive sculpted channels, like oversized channel scablands. So there have been there have been catastrophic mega floods that have passed through what is now the English Channel. The floor of the English Channel has scablands on it. Now, I don't know when that was. The one estimate I saw for an age on that put it too early to be, around the Younger Dryas, either before or after it. So I don't know. But right where your cursor is there, that channel through there there were catastrophic flows coming through, and down below where you see the green, I think that come over there to the left, stop right there, and then you're going to see two troughs where the green. There we go. We're zooming in. Those are probably some of the melt. Yeah. You're looking at the meltwater channel right there. You can follow it right up. Yeah.
Like this?
Like there. Yeah, you're in it now. There. That's it. That's exactly it right there.
Yeah, sorry for the low resolution, guys. This is a SketchLab file, but I think we can all see it.
Yeah. And if you pull up Google Earth, we can see it very plainly. But what this has a great job of showing the extent and volume of the ice complex during the late glacial maximum. And so you can see there that the Fennoscandian, which is the biggest one, the one over Europe, bigger than Greenland, that all would have either drained into the North Atlantic or into the Arctic. But draining into the Arctic, ultimately it would have flowed into the North Atlantic. So one of the ideas is that the Younger Dryas was caused because you had this gigantic meltwater flux into North Atlantic, and this, because the salt water is more dense, it created a stratification, and so you had this freshwater lid that shut down thermohaline circulation, which was bringing the warm currents up. Up into the area around England and Scandinavia. Yes, that's exactly right, what you just did right there. And then, so you've got the warm water coming up. It loops around right there where your cursor is, and then dumps its heat. And then as it cools off, it gets denser, so then it plunges down, and by the time it gets to where your cursor is, it's now deep water. Anyways, the idea is that the Younger Dryas was caused because you had this huge influx of meltwater coming from the Laurentide to Greenland and the Fennoscandian ice sheets, all melting rapidly. This interrupted the thermohaline circulation, which then interrupted the delivery of heat up to northern Europe, and as a result, it plunged back into cold, and this was the cause of the Younger Dryas, and why those researchers back in the 1800s noticed that the Dryas octopetala flower was there, then it was gone, and then it was there again, and then it was gone again. And they figured out that there were two periods that they called the Dryas, because it's Dryas octopetala. That's the name of the plant. It's an 8-petaled flower, and we can look at a picture of it. Well, in fact, Mike had the Dryas flower on the graphic that we looked at. Yeah, that's it right there. That's Dryas octopetala right there.
And so you're doing a web series on the Younger Dryas soon.
Yeah, I decided it would be fun to put out there. I can remember 25 years ago talking about the Younger Dryas, and nobody said, "Oh, the Younger Dryas. Yeah, I've heard of that. I know about that," or whatever. Now, I think we could safely say millions of people are familiar with the Younger Dryas. And I thought, okay, let's put out some history and explanation about the Younger Dryas. Now, there's a lot that I don't know about the Younger Dryas, but I know more than the average person. So I thought I'd take and put something together, and I've got two parts. I've got all the research, which is going to be part one. Maybe we'll call it season one. We'll go up from the beginning, the work of going back to the 1850s, 1860s in Denmark, coming up to the year 2007. Why 2007? Well, that to me was sort of a major turning point in our thinking about the Younger Dryas, because that's the year that the Firestone West Kennett paper was published, invoking the idea of an extraterrestrial impact being a trigger for the Younger Dryas and the mass extinction of the Megafauna, which more or less happened pretty darn close to each other. I mean, to the point where it's to me impossible to say they couldn't be related unless it's just purely a coincidence that you had this massive flooding, massive climate change, and the extinction of the megafauna, but somehow not related to the other things. So your question is I'm trying to develop a holistic model that encompasses all of these things that have. I'm just trying to come to. I've concluded, Stefan, that from the research that I've seen and done, and this is, I think we talked about this a little before, is that habitat loss is going to be directly related to loss of species. In fact, loss of species is kind of a measuring stick, a yardstick for habitat loss. Well, habitat loss is going to also be an indication of some kind of major environmental change. I mean, it's one thing if you've got local or regional habitat loss, but it's something altogether different if you're talking about global habitat loss. And we basically see the imprint of the transition from late glacial maximum to the Holocene is clearly a global event. We could even say a series of global events. The meltwater pulses 1A and 1B are both associated with other phenomena as well. And those phenomena have pretty much a global signature. Obviously, more intense, higher degree in some places, lesser in others. For example, if we look at the distribution of species loss, we see that North America, I think, squeaks in with the highest number of megafaunal species loss. Very close to South America. About 75%. About 75% of all species over 44 kilograms in body weight, which is the definition for a megafauna, went extinct in North America. And I know you know quite a bit about that. You know that there were
the North American lion. Like, we used to have lions roaming around, and
camels. 4 species of proboscidean that inhabited North America. Long nose elephants. You had the mastodon, which was a browser, was very prolific in the eastern woodlands south of the tundra, because most of south of the ice sheet for a couple of 100 miles was tundra, and then you got into where I'm at now in Georgia, which is a very temperate climate with a mixed ecosystem, was boreal forest. I mean, to find a duplicate of where I live now, you would have to go up to northern, like say up northern Minnesota, southern Canada, that area. And roaming around in those boreal forests were mastodons. And then in the open,
this is you 12,000 years ago.
That was look at that guy. Okay, so anyways,
when do you think that will be available for everybody? At least the first episode. That's coming out soon.
Oh, the first episode's out. Yeah, we did a pilot, and now we've recorded 4 clips. We're keeping the clips shorter. I'm trying to not get too diffuse. So focus on, the first one was just mostly talking about there was the pilot, and then the first one was about 25 minutes, and I'm just talking about basically the discovery of the flower in Denmark and in Scandinavia, and the Swedish scientist who made the discovery and first figured out that there had been a climate oscillation, because there was a layer of glacially deposited clay. Then there was a layer of what's called gytja, G-Y-T-T, gytja. Can't picture how it's spelled, but
C-H-A, gytja. I'm not sure.
It's like that. It's well, hell, I have
Jamie,
it right
pull
here.
it up.
It's a Swedish word. I'm pretty sure it's a Swedish word. Okay. Anyways, what it is, it usually forms in ponds and could be a cold environment, but still maybe not a glacial environment. So there was a layer of glacially deposited clay, what we call glaciofluvial, which means the dual operation of glaciers and water, which usually means water flowing under the glaciers subglacially, but it can mean water discharging out, whatever. If the water, So glacial fluvial usually implies that whatever you're looking at was created as a combination of ice and water. Anyway, so you've got this glacial fluvial clay. Then you've got the Gitcha, which means with completely different flora in it and fauna as well, because there's really no fauna or flora in the except for the leaves, the remnants of the leaves of Dryas octopetala. Then Dryas octopetala is not present in the Gitcha, which is formed clearly in a much milder climate, and then there's another layer of glacial fluvial clay. Now, in those two layers, you've got extensive remains of Dryas octopetala, which is growing very close to the glaciers. And then between there, you've got virtually no Dryas octopetala. So that's basically what he saw. He said, okay, I can find all these specimens here in this stuff that we know is glacially deposited. We could talk about why they knew it was glacially deposited, but primarily there was multiple reasons. But the point was they knew it was glacial. They knew that the Gitcha was interglacial, and then that was capped by another glacial. So that top glacial was the Younger Dryas. And then the Gitcha was probably going to be the Alarod, the Balling Alarode warm period, because the Balling Alarode fits the model of Milankovitch. If you start looking at the uptick in temperature that occurred in the Balling Alarod, completed at the beginning of the Holocene, and you take the Younger Dryas out of there, you take these oscillations out of there, it gets this nice smooth curve that's consistent with Milankovitch. But there we go. There we go.
Gitcha. It got us.
Yeah. Gitcha refers to sediment composed of partially decomposed plant and animal remains, along with fine non-organic sediment deposited in standing water. So this is a thing that you're going to find a lot of times, like in ponds. You know, it could be a pond, the standing water. But you're not going to find it in a glacial environment. If you've got water under the glacier, it's not going to form what you've got in Gitcha. It's going to be purely just pretty much mineral content. I mean, there will be flora and fauna in it, but they will be of a very different type. So, anyways, what you're looking at there shows very clearly the coastlines, not the coastlines, the continental shelves. Now, typically the drop-off point from the continental shelves. Now, there's the Azores microcontinent. But you can, if you look at any of the continents, like over there to Europe, and you see the light blue. Okay, so that's what we were looking at before. That's the North Sea, and you see the English Channel that's coming out down between France and England, right in there. Yep. So that was a catastrophic discharge right through that area, which is now submerged. And of course, so the point is that when you drop sea level 400 feet, Ireland and England become part of the European mainland. So that's a very different environment. And you can see where the shelf is, where the plain drops off into the deeper. That's at about typically 600, 700 feet. So there would have been a coastline that was minus 400 feet, which is not all the way out to the edge of the shelf there. But oh yeah,
Close
look, there's
to it.
Yeah, close to it. Look, there's a submarine canyon over directly to the left. Go left with your cursor right there. Now, so that was almost certainly part of the process of catastrophic downcutting. That water, you can actually look. You can follow it's subdued, but you can go right up to the north above that thing, and you can see the pathway of the water was following go back to the head of that submarine canyon there, right up to the head of it.
To really zoom in?
Yeah, now go up with your cursor. And
I see.
There it is. It's right there. Now that looks like it's the remnant of a flow. You see there's a topographic transition there.
Yeah.
So the water was undoubtedly following that ridge, that change in submarine elevation there. Then it accelerated in velocity as it approached the edge of the coastal plain there and then when it accelerated in velocity, it became more erosive and it started exerting shear forces on the ground and quickly downcut that submarine canyon right there. And submarine canyons are one of the really interesting features that kind of are just now only being processed and understood. You can see, oh, look, there's a beautiful example of a braided right over there to the right in there. Yeah, look at that. Now those submarine canyons are difficult to explain because for one thing, obviously you're not going to have the same kind of currents if it's submerged. Yet the indication is that there were tremendous shear forces being manifest in these currents because they were able to carve out and move a lot of material. It almost seems, wondering if, my mind, could it be, ancient tsunamis that are ultimately responsible for that?
I do find it interesting. I love looking at Google Earth because this topo data gets better every year.
Yep.
And even like the low resolution stuff, the global coverage tells quite a story. And then more and more places are getting high resolution coverage, for example. Like you see these tracks now have higher resolution. But it really is making things clear. And if you have a macro-based mind, this is like really key stuff. For example, seeing that land bridge and noticing, oh, that's going to just cut off the ocean flow between the Pacific and the Atlantic. That's a big deal.
That's a huge deal.
Learning that there's a massive supervolcano up here is very interesting. That's Glacial supervolcano. And you're talking about ice sheets earlier and glacial fluvial processes. And I don't think many people fully realize how quick that can be.
Oh,
that
yeah.
Once these ice sheets and glaciers are lubricated, they can discharge really rapidly. We see that with Heinrich events. And because they carry along some sediment and ground up rock with them, and these icebergs then basically will melt in at least in this case, the North Atlantic, deposit those special sedimentary layers, which then we've done tons of drill cores across the Atlantic and other oceans, of course, and detected these Heinrich events are quite frequent. We're actually effectively in one right now. People may not realize that while most of the planet is warming, the one point on the planet that has been cooling over the past 50 years is the North Atlantic because we keep getting icebergs to melt there. It's not by much. It's by like a half a degree Celsius. But it is quite interesting. But here, like if you look at this, the drop-off is pretty quick for the Azores. If you look at the topo map, it's like 1,000, 2,000 meters. But so you look at that like, oh, well, 400 feet, 125 meters is not enough to explain this being basically like a microcontinent, you could say, or like a large island. But if there has been subsidence there, as you're speculating on, then that could explain it. And that's interesting because it's a triple junction for basically plate boundaries and stuff. You have the Mid-Atlantic Ridge, and then you also have just like this kind of continuation here.
That's it. That's the plate boundary right there. So above that is the Eurasian plate, and below it is the African plate.
Yes. So if we do that, there we go.
So that's it right there. You can actually see it, and then that's and then the Mid-Atlantic Ridge, which generally is kind of north-south oriented. To the west of that is the North American plate. So right there, the Azores Plateau flanks that triple junction, and that triple junction would be the natural place for the energy to accumulate that could cause a significant subsidence.
Yeah, we know there's a lot of water in the mantle. Because it's bound up in like OH bonds, and there are some estimates that if you were able to take that water out of the mantle, you could actually increase sea levels by like double or triple. Now, what's the mechanism for that is a good question, but there's water getting into the deeper parts of the earth and then undergoing these mineralogical changes and being bound up in OH bonds and such. And where's that water coming from? My point here is I think there's a lot more water flux from the deep earth to the surface than a lot of people think. And places where the plates are, it's like not like a solid crustal plate. There's a triple junction would be the perfect place for there to be some flow of water going down. And that's going to pull things with it, I would think. But this is speculatory to some degree.
Well,
speculation.
It's interesting speculation. One of the things that's immediately coming to my mind is the changing surface pressures, the changing loads on the surface will cause lateral movement of that subterranean water, if you want to call it that. So picture this. You've got this huge ice sheet like we were just seeing in the previous graphic. That's rapidly removed. Right. I mean, think about that. That ice sheet is, within 5,000 years, most of that ice sheet is gone. And the deglaciation process was not smooth over the first, like, let's say, the first indication of meltwater influx into the oceans. And then the point at which the final deglaciation phase occurred, which regionally it was different because you had some areas where the ice melted faster, others where it lingered longer, maybe up to a millennium longer. But most of the ice was pretty much gone by, say, 7,000 to 8,000 years ago, right? So you had huge masses of dead ice. Now, the thing is when you're looking at this, you almost have to think of this as like, I call it like living ice, living glacial ice. Why? Because it's being fed constantly in the zone of accumulation. It's a flowing integrated system. And then it melts, it dissipates at the zone of ablation. And there's this balance typically between accumulation at the top end, ablation at the bottom end. It can be influenced by changes primarily in temperature, also changes in precipitation. So what happens is, if you increase the amount of accumulation and you don't adjust the zone of ablation, the glacier grows. Let's say you increase the temperature. So now the zone of ablation, the melting at the snout of the glacier increases in rate. So now the glacier shrinks. That's what we've been seeing over the last roughly 150 to 200 years. But that's a balance in between there. Now, you look at that right there, the only mass of ice that still remains is what's over Greenland. I mean, that's it. All the rest of it's gone.
And that's a huge amount.
That's a huge amount. And people don't, I mean, that's more than taking the entirety of Greenland as it is today, plus the South Pole ice, and melting that all. And the final point I was going to make about that full deglaciation phase from the first melting, which I think is going to end up being right at 14,700 years ago, maybe just preceding the Milankovitch forces preceded meltwater pulse 1A by maybe a millennium or two. So you start seeing that upward curve in the melting rate and the initial rise of sea level. Then you had this big pulse. You had this flux of water that accelerated way beyond what you would expect from Milankovitch. Then it tapered off again until the beginning of the Younger Dryas. However, it continued to rise throughout the Balling-Allerode, which was roughly from that 14,700 to 12,900 years ago. Then that transitioned to the Younger Dryas, which 12 to 1,300 years. The Younger Dryas gave way to the Pre-Boreal, which was the first stage of the Holocene. And both of those events, those environmental climate change events that bracketed the Younger Dryas at the beginning, which actually is at the bottom of the sedimentary column, and the top of it, both of those were catastrophic.
Yeah.
And both of those caused major disruptions to the biosphere. And to the hydrosphere, and obviously to the cryosphere. Because when you're looking at this here, that's a very, very, very different world from the one we inhabit.
Yeah, I don't think it's easy to wrap your mind around in any sense.
No, it isn't.
I think you've done a good job of it just because you spent so much time thinking about it. And I think one reason a lot of people like you is because you've also done a lot of the field work of just going to hundreds of sites around the world and just seeing it with your own eyes, which is an important thing to do. And so I think the other thing with the Younger Dryas impact in terms of why people are so interested in it, not only helping to explain our history and cataclysms and how that is a influence on the earth and species and everything, but it also provides like a doorway into a whole bunch of different things. For example, talking about the movement of water and mass around the planet, like how does that influence plate tectonics? This seems to be a neat pathway into discovering maybe some new corollaries that we should be adding on to global plate tectonics that currently maybe isn't really discussed too often or taken seriously or just not well known or even thought of yet. That seems to be a very important thing because we know plate tectonics exist now. We have the GNSS measurements of the plates moving around, but there seems to be more variability of expression for plate tectonics in my mind. This is my intuition than we currently think. Right now, it's just currently they're butting up and subducting or they're splitting apart and that's it.
Right, and I think that what maybe the part that we're going to be amplifying over the next few decades is understanding. I mean, we've come a long way with understanding the lateral movements, continental drift. We know what a spreading boundary is. We know what a convergent boundary is. We can see those effects. What I think we're beginning to appreciate now, though, is the isostatic component, the vertical movement of the plates, and that is a much more extreme phenomena than had been appreciated. And I think, interestingly and ironically in a way, I think that's what the Atlantis story, not all the fanciful stuff that's grown up around the Atlantis story, but Plato's actual account, which I think whether you consider it all just an invention, a metaphor, or all all truth literally, or somewhere in between, that Plato meant that he actually drew upon some historical precedent to build his philosophical concept of the ideal socio-political state, which is basically the position of academia, and there's no literal reality to the existence of any Atlantis, 11 or 12,000 years ago. On the other hand, you've got, at the other end of the spectrum, you've got the true believers, and, they're the people who will say, yes, I'm reincarnated from an Atlantean master.
They're an Atlantean priestess from 12,000 years ago.
Yes, I've met a few of them, actually, over the years.
Oh, they're great.
Hey, I'm not knocking Atlantean priestesses, okay? But there's two ends of the spectrum, right?
Yeah.
And then there's lots of gradations in between. One of those gradations would be, okay, well, we can't take all that stuff literally, but there was some kind of historical precedent that Plato drew upon. The typical one that's most frequently invoked is the eruption of Santorini in the Mediterranean, or the destruction of the civilization on Crete. There it is. Yes, there it is.
And just this year, there was a huge magma intrusion here on January through February of 2025. And everyone was saying it's just a tectonic event. And then the research came out, like once all the data was there, like, oh, a huge magma intrusion came up from this volcanic system here, and telling people, guys, these things still exist. It's not like we're on a planet that has nothing exciting ever happening. Like, it can happen.
It's still a dynamic planet.
Very dynamic. We just are in a quiet period right now. In the big sense, in like the really big sense. But speaking about Atlantis, I would like to ask you about the Richat Structure, just because we see it right here on Google Earth, and I have an interesting observation to present to you, and I'm sure you've talked about this a lot, and I'm not here to say Atlantis is the Richat Structure. I'm so open on all these ideas. I have not made any firm decisions on it because I don't.
This is commendable. You're keeping an open mind.
I think
Yes.
everything is very interesting, but we have a magnetic anomaly located exactly at the Richat structure.
Oh, I
So,
believe that totally. Yeah, I totally
so just
believe
what are
that.
your thoughts on that? What are your thoughts on the Richat structure? Because this is odd that we see this one of the largest crustal magnetic anomalies in the world, effectively right on the Richat structure, which looks like some sort of impact event to me. It's very odd geologically.
Yeah. Well, it has been actually, and I tend toward just that it's been the paper. When did it come out? 2014. They had done some subsurface exploration and showed that it is some type of an ancient magma event, but that has been altered by hydrothermal phenomena over the millions of years. It was originally, I think, the date that they put on it was Cretaceous. I could pull up something here. Let's see about the study of it. Okay, here we go. This was from the Journal of the African Earth Sciences, 2014. Hydrothermalism. So hot water, right, played an important role in the evolution of the Richat complex. It is responsible notably for the karst collapse central megabreccia formation. So you know what a karst is? Okay. So a karst so beneath it there's a karst-like phenomena that had a lot of hot water flowing through it. Now we're talking about probably in the late Cretaceous.
These can be like void structures for anyone that's listening. We see karst, for example, like Santa Cruz, where there's a lot of limestone and such. And
Limestone,
as a result,
yeah.
there's a whole bunch of caves in that area.
Right, because any carbonate structure rock is going to be soluble in acidic water. So if water is flowing through limestone terrain, it dissolves. Limestone will dissolve in water chemically. Now, you can have other type of rocks, like say granite will dissolve, but it'll dissolve mechanically. It won't dissolve chemically. It'll be turned into sand, whereas the calcium carbonate in limestone rocks becomes a part of the solution. So anyways, you've got this thermokarst structure beneath the Richat structure. Let me go on here. So you have a karst collapse central megabreccia. Megabreccia is just simply broken rock. So megabreccia means you've got big pieces of broken rock. And a karst collapse so it eroded underneath. Imagine, like you were talking about, that the limestone terrain gets dissolved and creates a void beneath this. It collapses. It collapses into this. And so that's right there in the center where that megabreccia structure is. Let's see, the alteration sequence of the rhyolites, the potassic alteration of the gabbros, and the gabbros are what formed the ring structure, and the stable isotope enrichment in the carbonatites. Let's see. So let's see. Basically, these studies of it show that it's an igneous complex, and then below it, I could actually.
And that would make sense with the magnetic anomaly, but it must have been a big volcanic igneous event to create that, because there's not magnetic anomalies like that everywhere. We have one here
Correct.
called the Bangui magnetic anomaly, as we see right at the beginning there. That's a big one. And this Richat magnetic anomaly is similar, comparable in many ways.
Well, and something that's interesting and may have something to do with this. Let me share screen here for a second.
Sure.
And then we'll come back to you. This is I'd never seen this before, but that's really very interesting. But that doesn't make the case that it's Atlantis. Now, if it was, for one thing, the rim of the structure is 1,500 feet above sea level, so that's not consistent with Plato's account, where he very clearly talks about Atlanta being an island that subsided. So there have been large flows of water, no doubt, over this terrain. You can actually track that's most likely what eroded the structure in the first place.
Nicely.
Yes, there you go. However, there's something you can't see here. And when let's see, so I am going to share my screen, I don't know. Do you
Yeah, I really see the Richat structure as being an oddity. So whatever it was or is, or the history of it, regardless, it's like the more you learn about it, the stranger it gets.
Oh yeah,
It's already weird, and then you learn about the magnetic anomaly. Like, okay, this is getting even more odd.
Okay, so we have the Temi. I'm not sure how to pronounce it, but it's a crater. It's an impact crater in Mauritania. And if we go to the next slide, we have another crater, the Tanum. I did actually look these up and learned how to pronounce them once upon a time, but I've forgotten. Anyways,
Factor in the Younger Dryas.
well, these are much earlier than the Younger Dryas. And of course, they're circular structures with rings, but the rings are pretty intact when you look here. But the interesting thing is this. The I learned how to pronounce this. The Tememichat crater is here, and then the Tunumer or whatever crater that you see is here. And here's the central Megabreccia complex that is the center of the Richat structure, and they are in a perfect alignment. Now, is that of any significance? I don't know. Other than the fact that, remember we talked about that 38th parallel? The same idea there. If 3 of them, of the 8 or however many it is now, turn out to have been basically proven to be impacts, the others are being called crypto explosion structures because are they impact produced from the outside or are they volcanic? And I think, well, why can't it be both? I mean, if you've got 3 big impacts, I mean, what's that going to do to the crust? The lithosphere, I mean, it's not outrageous to think that you might get a crack, a large fracture, or even a fault line as a result of like a multi-impact event like that. So I don't know if that's what's going on here. And it'd be interesting to see the dating of these 2 impacts. Yeah, there you can see the line.
Yeah, it would indicate they're connected, that something flew in and there were different elevations to some of these pieces. And so you get 1, 2, and then 3.
Yeah. But there is no, when the Richat structure was first discovered, and that's where I first heard about it, years ago, because it was proposed to be an impact structure. And then they did studies and they said, well, there's no actual evidence of a hypervelocity impact. You don't see any shock quartz. You don't see any micro evidence that they could find. And so they decided then that it was an endogenic rather than exogenic. But here's your kind of your cross section. Let me see. I think there's a better one here. Let's see. There, those. So that's the ring gabbro structure. So if you can picture this, before we get to that, let's go to here. If you can picture, Stefan, if you got a flat area, now you have upwelling pressure like a plume below it, and that comes up and it causes a domed uplift, right? So you've got this, it's like a dome, right? And you've got the stratigraphy in there, you've got the layers. Well, then once it's domed up, now you visualize you come in and you truncate that dome, and the exposures of the stratigraphic layers are going to be ringed. They're going to be circular. You can picture that, right?
Yeah.
I mean, I'd like going to create a model of that at some point to just because it's. Let me see if I've got a simple piece of paper here, something that I can show. A dome.
We have other geologic examples of this around the world too, so it's not necessarily unique. It is unique in terms of how it looks and popping out from space, but we do see smaller scale, at least I know, that you can see that at play.
Let's see, do I have, here we go, let's back up. Okay, so coesite, so there was, let's see, this is 1969, so I think, coesite is a high-pressure polymorph of silica, which only occurs in the kinds of pressures produced by hypervelocity impact. I believe actually coesite has been found as a byproduct of atmospheric nuclear weapons testing. I'm not 100% sure. I think it was, though. So the shattered sandstone from Richat reported to contain coesite. after a scientist, a geochemist named Lauren Coes, I think, Coes. He was the one who discovered it and studied it. A tectonic breccia probably represents a shear zone developed during the structural doming. An optical and X-ray examination of concentrates from this breccia demonstrated that the supposed X-ray reflections of coesite are actually due to barite introduced into the permeable crushed zone by groundwater. So there we go. We're talking about water again moving through, groundwater moving through, because if you fracture the bedrock, you've now created all kinds of conduits for the flow of subterranean water.
And there's huge groundwater reservoirs in Africa, specifically North Africa. It's just underneath the Sahara now, but they're vast.
And that's interesting. That is very interesting because that undoubtedly accumulated, or at least was recharged during some of these temperate phases of North Africa and pluvial periods, rainfall periods. And we know that the bedrock is permeable. So it would make sense that when you have copious rainwater, you're going to have percolation down into some level, and it makes total sense that you would have a groundwater reservoir in Africa. So let's see, we got a color. Okay, so this shows the magma, and there are apertures to the surface. And you'll notice, let's see, one of these is really good. Here we go. So this shows the likely, more or less, evolution of it. So you see these, where these plumes are coming out here, these discharges, atmospheric subaerial discharges here. These are the cross sections of the rings. So here again, you see the layers and then the doming uplift. And if you were just to draw a line across this and get a section of it and then look at it from above, you'd be looking at a ringed structure.
Yeah.
The hydrothermal breccias is this. So that, let me see in mine, they don't show up quite as good here, but so here it's got this lid of sandstone on top of the limestone. Here's where your limestone is. So go to the next one. And then the collapse starts. So these are rhyolitic magmas down here. This is your magma chamber. And so it's extruding up these these conduits here. Let's see what we got. So yeah, basaltic so you got the basaltic magmas, the solid gray, and then the rhyolitic magmas are the crosses here. Let's see here, hydrothermal fluids by these open arrows. So hydrothermal fluids are being pressured, are flowing under pressure up through the rock. Let's see here. Yeah, your basement rock is all of this. Let's see. Then you go to the next one, and you can see how the whole structure is collapsed down into the voided magma chamber. Okay, so this is, I think, going to be the final phase. Now it's eroded down.
And some sedimentation, yeah.
Yeah, and here, yeah, so here's your breccia. This is basically your big pile of broken rock right here. And, okay, and then you've got this cap rock of sandstones in here. Let's see. Was that all that I had on that?
The Richat structure would be a crazy geology field mapping trip. That'd be wild.
Yes, it would. Well, Stefan, get busy. Set it up. Can you set it up for March?
Is that the best time of year to go?
Oh, I don't know.
The only time when it's not going to kill you from the temperature?
No, yeah, that's a good point. Okay, so if somebody asks you from now on, Stefan, you just tell them, hey, it's an isolated Cretaceous alkaline hydrothermal complex.
That's easy.
Get out of here with all that other Atlanta stuff. It's an isolated Cretaceous alkaline hydrothermal complex. Come on. You didn't know that? Jeez.
So you're really interested in putting together a more universal, comprehensive picture of the Younger Dryas, because that was likely just our most recent example of something like that that's occurred in its own, in their own variety of ways, but all similar signatures probably. hundreds or thousands of times across history.
Right.
And so that brings into account learning about the geology and the hydrosphere, of course, plate tectonics, all this, but also the interstellar environment and what we have coming in from space. And also, we've talked in the video that we did on your channel. I'll link that below, folks. Also, I'll link your Younger Dryas season that we talked about earlier. I'll link that in the video description as well. But this interstellar environment seems to be a pretty important piece of this puzzle, because at least it provides a explanation for like the trigger mechanism for how you destabilize the ice sheet.
Right. Well, so let's go back to the model that has been the dominant model of the Younger Dryas, the cause of the Younger Dryas. I mean, going back decades, going back literally to the 50s and 60s, when that idea first started getting proposed, that it was an interruption of the thermohaline circulation, right? That interrupted the delivery of warmth up to the northern latitudes, like up by England and Scandinavia and so forth. And that was what triggered the Younger Dryas. Well, okay, but to me, that's tautological, because you got to say, okay, so, you know, there's concern now, I think completely unfounded, about that happening now, because, you know, there's a school of thought that says, well, we know it's likely that the thermohaline circulation was interrupted by these gigantic volumes of glacial meltwater discharging into the North Atlantic. It completely disrupted the current flows throughout the North Atlantic. Sure, totally makes sense, right? Now, in the modern version of that, the discharge primarily from the Greenland ice sheet, that is the concern, is that, okay, that's going to do the same thing. It's going to interrupt the thermohaline circulation and cause major climatic changes. However, the differences in volumes are orders of magnitude, right? It's one thing to say that a discharge of 10 to 20,000 cubic kilometers of water per year or more, probably more, is in any way comparable to what we're seeing going on today. It just doesn't make sense. So there is, to me, a definite role for the interruption of basically what is now the Gulf Stream current, right? However, to me, that's a consequence. It's not the initiator of the process. It's a consequence of whatever triggered, because obviously you're creating huge amounts of meltwater rapidly from what had been glacial ice for thousands of years. Well, in order to accomplish that, you have to introduce heat energy into the system. Whence that heat energy? It was actually even first identified as a paradox in the early 70s. In fact, it was called the energy paradox. Because at the point you had in the early 70s, you know, radiocarbon, you had accumulated 20 years of radiocarbon dating. What's his name? The inventor of radiocarbon dating published his first paper on it in 1952. But, you know, there was a lag time between realizing that we could date things by the radioactive decay of carbon atoms, between that realization and the publication of that paper and the actual collection of enough data that you could start to make inferences from it. And by the 70s, though, it had become apparent that the rate of disappearance of this gigantic glacial mass had happened a whole lot quicker than anybody had imagined, right? So then the scientists looking at it then asked the question, well, whence the energy that caused this rapid melting? And
rapid, it's like the key word, like really rapid on the
really
geologic
rapid,
times.
really rapid. And this was what they called the energy paradox. They had a conference where they discussed it in 1973. Then they had a follow-up conference in 1974. And the result of these two conferences was they didn't know. They admitted at the end, we don't know. We don't know what this is. And then it kind of got put on the shelf and forgotten about. But very few people have been asking that question, that if you're going to melt all that ice really quick, You got to introduce a lot of energy really quick into the system. Now, they did a simulation and asked where on the planet today would you have enough heat energy to melt that ice in its totality as rapid as they knew had been estimated by the early 70s, right? Where on the planet do we have the most available heat energy? Well, there were two places they came up with, the Sahara and equatorial tropics, equatorial ocean water. Here was the problem. They took the energy at both of those places, which were roughly the same, and they realized that even with the total energy flux, let's say of the the mid-equatorial, the equatorial region of the Atlantic Ocean, it would still take 3 times as long to using the energy available at the equatorial oceans to melt the entire ice complex.
And there needs to be some route of transfer for that energy too. That's rapid.
Yeah, I mean, the idea is that if you took the entire ice mass, rotated the Earth so that it was now at the equator, it's still going to take tens of thousands of years to completely melt away.
I see.
You're looking at 6 million, minimum 6 million cubic miles of glacial ice. So, I mean, I ask people, okay, let's go outside here and visualize what 1 cubic mile ice cube would look like. A mile over your head, a mile this way, a mile that way. And let's say we could instantly melt that 1 cubic mile ice cube. That'd be a hell of a big flood.
Oh, yeah.
Well, now you got like 6 million of those. And you got 10,000 years to get rid of them, except that within that 10,000 years, it's not a uniform process. It's punctuated by short periods of massively accelerated melting. And that's pretty much the model that we've got now. So where is the energy source for that? Like, where's the energy source for Meltwater Pulse 1A? Where's the energy source for Meltwater Pulse 1B that came at the end of the Younger Dryas? We don't know. I don't know. I was hoping you'd know and could tell me.
I'm new to this. I'm very interested in all this, and I'm researching as much as I can, but I don't have all the answers. But I do think we have some clues in space. Comets and asteroids, and learning about that has been really fascinating, and I think redefining our understanding of Earth, its history, geologic processes. I want to get your thoughts on the clustering of trans-Neptunian objects. And I want to run just kind of an idea I've had by you. So we have not detected all of them, of course, because we really only pick them up when they're close to their perihelion. If you look at the top right corner there, 2014 FE72 has it goes about 4,000 astronomical units out. So its aphelion is like 4,000 AU away from the sun.
4,000. Okay, let's try to get our heads wrapped around what that means. 4,000 AU. So we're talking about astronomical units, which is the distance from the Earth to the sun. So that's 93 million. And you're saying 4,000.
That's the estimate. It's a
So
92,000 year orbit. Neptune, going to Neptune, folks, is 30 astronomical units, and that's way out there.
That's way out there. So how is this thing at that distance bound to the sun?
That's kind of the question. And so we look at this, and you see this. I think they don't have it shown in this one. There is a hypothetical Planet 9, Planet X, that a lot of astronomers now are hypothesizing exists to create this clustering.
Okay.
I also am just as interested in the idea that we have an ultra-wide binary star companion that has like maybe it could actually account for precession, but I'm not sold on it, but it could maybe have this 24,000 year orbit, and when it swings in close, though they still remain pretty far apart in the grand scheme, that could then cause a lot of instabilities to the Oort cloud, or at least our Cometary reservoir, and cast things in. But the orbit of Sedna, for example, which is colored there in that like light pink color, like that peach
Yeah, I
color
see it,
on the
yeah.
right side. That is a 12,000 year orbit. And Sedna right now is going to have its perihelion 2076. And last time it did so was right at the basically Younger Dryas. A little bit before, it was with the Göbekli Tepe. So right after the Younger Dryas ended, Sedna was at its perihelion. But I just look at all these objects. The question I want to run by you is, I look at all these objects and I think of them gravitationally as the sun has a strong gravitational field, of course, and that extends obviously way out. But in their local zone, these objects will have a stronger gravitational field than the sun because they're right there. The wave falls off with inverse square law. Yeah, and so some of these objects are going so far out there that if they're swinging in, I just get the sense that they're probably agents of disruption for some of these other objects like comets that are only very loosely bound to the sun.
Right.
And that could cause them to fling in. And it could perhaps, if there is a clustering to these trans-Neptunian objects due to either Planet X or Planet 9, or let's say a binary dwarf companion for the sun. I have a more kind of complex view of that theory that's probably a little beyond right now to share. We'd have to spend some time on it. But if there is a clustering of them coming into perihelion around the same time, then they could almost create like a wave of disruption, bringing stuff in. And that could perhaps explain why we get a bit of a rhythmic cycle to these things. There's not a perfect 100% like this is the yearly rhythm, like it's every this many thousand years. But there does seem to be kind of a regular occurrence of them that has some cycle to it with some variability.
I think we could safely call it quasi-periodicity. That's what I'm trying to say, quasi-periodicity. And what you're saying to me makes sense, that I think we have to look at some disruptor of the quasi-stability of the comets in their respective reservoirs. And something is doing that. Now, I mean, we could invoke various things. I mean, a nearby supernova explosion. That would not necessarily induce any kind of periodicity, I wouldn't think, right? Because, you know, it's a singular event. Whereas an orbital system like you're talking about, yes, could induce periodicity. If that is the thing, some large orbiting object is disrupting the very delicate gravitational bonding of these objects in the Kuiper disk or the Oort cloud, and send a cascade of objects towards the sun. And now, of course, once it gets to the Jovian orbit, Jupiter's going to probably throw half of them back out, but there's going to be a high percentage of comets that leak through, and they're going to get captured into short period orbits if they're originating from the Kuiper disk. And if the final manifestation of these outsized events is imprinted into the Earth, well, I mean, obviously, if this object is in an orbit, it's going to be very regular. But then the consequences of that, if it's dislodging comets that are now falling towards the sun, themselves going through a hierarchy of various levels of disintegration, spawning subnuclei, if you want to call them that, well, now the accretion rate of that to the Earth is going to have a rough periodicity to it. Yes, it is. I think you could pick up the signal. What we would probably, in my mind, be looking for is look at evidence for impacts on Earth that are clustered. And that would suggest to me, if you've got, rather than stochastic or just randomly through time, you've got clustering of objects, that would suggest, well, there's some greater phenomena that is inducing that clustering. So an orbital object like you're talking about, to me, would make sense from that standpoint.
What's also interesting about Sedna, but these objects in particular, just all of them, is that if you look at the orbit of Sedna there, it is perfectly lined with the galactic center. So its aphelion, its furthest away from the sun, is towards the galactic center.
Okay.
And the constellation Sagittarius.
Yeah.
And then its perihelion is opposite that. So roughly constellation of Gemini in that zone. And I can just really quickly show that by doing one of these deals here. We see the center of the galaxy, and then we see this is Sedna right here, close to its perihelion, which will be 2076. But if you see that orbit going out like this, this is the sky live, you see how it aligns with the center of the galaxy. So if we go back to the other graphic now that shows all of them, you can kind of position them. You see that they're not all perfectly aligned with the center of the galaxy, but they are in general lined up more in that direction than away from the center of the galaxy, which would be towards the outer, like outside the galaxy, where there's going to be a lot less stuff in general. So these things coming in from closer towards the center of the galaxy, there's a lot more action, perhaps bringing things in with them. And that's also where 3i Atlas has come in from. It's come in from the constellation of Sagittarius.
Okay.
So it's like, it's just too many coincidences to kind of be like, I just think it's us all totally random. Like there's a lot of action clearly happening closer to the center of the galaxy, and we're having these waves of things, either these trans-Neptunian objects which are aligned with it and then they come in on their normal orbit, or in the case of 3i Atlas, this interstellar object that's flying in ballistically. It's unusual.
I would think so. So then, then we can safely infer from this, or confidently, that there is probably a galactic component to what ultimately, as it reverberates down through the hierarchy of phenomena, when it gets to the Earth, we have these imprints of catastrophes that do show quasi-periodicity. Mass extinctions, and I can actually show you some graphs here where that was showing up even back in the 70s and 80s, where you could see this periodicity to the glacial and it's rough. It's a rough periodicity, but it's still pretty obvious, right? Which would fit this idea, because the trans-Neptunian objects. Let me ask you: do we know the mass of Sedna?
So,
is that just their hypothetical at this point?
We have some size estimates and some mass estimates. The size is about 1,000 kilometers across. They're all kind of in this like 800 to 1,200 kilometer across range.
Okay.
Some are a little bit bigger, and then the mass is I think it's about like, usually it's more than water, which would be 1 gram per cubic centimeter.
Right.
But it's not like the density of the Earth. So I think it's usually like 1.4 to like 2 grams per cubic centimeter, but don't 100% quote me on that. But that's the given densities. Typically, I think it's like 1.4 or so.
1.4,
but
okay.
They have some rocky characteristics to them, but they're also very heavy with water and some of these lighter elements and compounds as well.
Interesting.
So they're not the biggest gravity players, but you put enough of them and you send them far enough out, and the gravity field is already weak. It's just a weak gravitational field from the sun stacked on top of the even weaker galactic tide, and then this thing comes in and maybe it's enough to disrupt something to all of a sudden zoom in, and as we talked about in our podcast on your channel, as something falls in closer to the sun, it's going to accelerate,
yep.
and get faster and faster and faster. And they'll be, these objects here are moving their fastest during their perihelion, and they'll be at their absolute slowest at their furthest distance.
Yeah.
And so anything they dislodge, if it lines up with this, they're probably creating, well, maybe not probably, but in this idea, they're probably creating like a shotgun effect where it's going to go all over. And then some of them will get sent to the inner solar system.
Right. And what you were just saying, you could almost visualize it like let's say if the sun is here and it's orbiting. Yeah, okay, so now it's coming in. As it's coming in, it's speeding up like this almost. Slow down, speed up, like that. And it's almost like a slingshot because it comes around and then it's thrown out, and then as it's coming in, it's getting this assist from the sun's gravity, and then as it's going out, it's getting a braking effect from the sun's gravity. And the farther it gets, the slower down it gets until it finally loses steam and then just starts falling back towards the sun. I'm going to do a quick share screen here. You'll be interested in this, I think.
Yeah.
This was actually, again, going back to the early 70s, and this was a temperature curve from surface water in the central Caribbean, which they're testing because by looking at the sediment, they can look at the flora, the fauna rather, that's living in the ocean water changes with temperature. Okay, even the coiling from of some of the animals, like the forams with their coiled shells, will reverse as the climate changes from warmer to cold. Anyways, this is from was published in the journal Science in 1973. Quaternary, which is the Pleistocene and the Holocene, right? Paleo temperatures and the duration of the high temperature intervals. And you'll see here what I'm talking about.
A lot of good research papers put out in the 60s, 70s, and 80s that seemed less encumbered than nowadays, where now there's some of these ideas are like so cemented in the public mind that you can't push against them. Whereas back there was like this, it felt like there was, just reading these papers myself, that there was a lot more just exploration of freedom and thought and idea.
Oh, I absolutely think, because for one thing, I don't think that science had become so politicized at that point, and it's thoroughly compromised now, in my opinion. All right, so what we're going to look at, Stefan, is a generalized temperature curve for the surface water, the changing temperatures of the surface water in the Caribbean. Now, of course, this is regional. Keep that in mind. However, we can now see from the 1970s, we can see that the signal is pretty much global. But it was apparently quite preserved quite well in the sediments, the bottom sediments of the Caribbean. And this is based upon the changing fauna that's in the water column, both benthic at the bottom and planktonic in the water column itself, which studies have going back decades and decades show that the species changes with the changing temperature of the water. Anyways, that's how this was derived. And let's see, I should have there we go. So this is the current temperature. So this is going back 400,000 years. And what it's showing is that the waters of the Caribbean oscillated between interglacial, which are these little peaks above the red line, and then the full glacial, which are the troughs, right? The numbers above the horizontal axis refer to stages. So here you've got, these are the stages. So this would be stage 3, stage 5. So the Eemian, stage 5E, it's called, which was a period that's warmer than now, is this spike right here. So stage 5E. So the stage 5 is then broken into substages for higher resolution analysis of the data. But what you see here, again, this is what I'm talking about, quasi-periodic. There is a generalized periodicity to this, but and of course we have much more resolution now than we had in '73, because the ice cores give us a much more precision year by year than this. But this still gives you a generalized impression that you have this oscillation between interglacial, which is the peaks, and full glacial, which is the troughs. And then you've got these
periodicity with like a 20% on each side, something like that.
Something like that. That's about what it looks like when you go by the timeline on the bottom here. So yeah, we're going 400,000 now. Let's say somewhere between right around here and here, modern humans are showing up. Somewhere in here, based on probably the latest dating, which I think conservatively puts Homo sapiens sapiens at 150,000 years ago. I think that's a safe assumption.
I think it goes back even further now.
Oh, yeah, I think that's why I said conservatively.
Oh, yeah, for sure.
And that was
really be sure, then
yeah. and that was the number I was using for years. And I think really now it's closer to 200,000. And I would be even willing to speculate before it's all over, we'll be seeing our species going back 250,000 years. That wouldn't shock the hell out of me. So that's a very interesting graph. Let's see, then.
And to think that civilization only developed once in the past 10,000 years, when we've had the same brain size for more than 100,000 years, and we've had multiple interglacial periods.
Yes.
If that is a requirement, who says that's a requirement? There's plenty of places on the globe that are still going to be warm during a glacial period. Just go to the equator.
Oh, yeah, yeah. Well, then since I've got this open, let me see if, I'm going to stop sharing here. I'll show you the Gulf Stream during the late glacial maximum. Okay, here we go. Let me reopen that. And see, this is why I say this would have been one of the probably optimum places to live during the late glacial maximum. Here we go. This was based on a study that, let's see, which came out in 1988 in the journal Science, and the title of it is The Position of the Gulf Stream During Quaternary Glaciations. In the present-day North Atlantic Ocean, the boundary between subtropical and subpolar gyres runs southwest to northeast from Hatteras to the northern Norwegian Sea. The warm Gulf Stream and its extension, the North Atlantic Current System, coincide with this boundary. In contrast, during the last glacial maximum, approximately 18,000 years ago, the gyre boundary and associated currents were more zonal and located further to the south. So here's the warm equatorial waters coming up and wrapping the Azores microcontinent in a warm embrace. I looked at that and I thought, that suggests to me that probably was not a bad climate during the late glacial maximum.
Yeah, I think there's something there. I think there's definitely something to that. I'm more on the Azores side than I am on like the Richat Structure side. But I can't really. I have a lot more research to do into it. But certainly, this seems to me that there's something there, and at the very least, the idea that you're going to have movement in the crust. We already see the isostatic rebound in North America, but maybe some sort of reciprocal movement somewhere else. That's also very intriguing to me. Well,
I'll just give you a little sample here. This goes back again early 70s when a lot of this stuff was first emerging, because again, We've had 2 decades now of data accumulating, radiocarbon, which has allowed for getting a much more accurate and precise chronological scale of this change, right? So this is in the journal Quaternary Research. It's titled Past Sea Levels, Eustasy, and Deformation of the Earth. Now, eustasy or eustatic sea level change is basically sea level rise and fall due to glacier expansion and contraction. Eustasy specifically refers to glacially induced changes in sea level. So when glaciers melt, you have a eustatic rise in sea level. When glaciers grow, you have a eustatic fall in sea level, okay? So this is Past Sea Levels, Eustasy, and Deformation of the Earth, by R.I. Walcott. I don't have a bio on him, but he was probably a geophysicist. So in a paper largely ignored in recent time, Daly in 1925 pointed out that changes in surface load over the oceans because of eustatic changes in sea level would deform the Earth. And according to Rudsky's 1889 calculations of the surface deformation of a homogeneous elastic sphere, this deformation would be of significant magnitude. In late glacial time, 18,000 years before present, the major changes in load originated from the melting of ice over Fennoscandia in North America and the simultaneous worldwide rise in sea level from the released water. Because the surface loads involve the lateral transfer of mass, so must material be able to move laterally at depth within the asthenosphere. The already complex picture of relative movements of sea level is further complicated by the ground movements due to post-glacial rebound itself. The material that flows into the deglaciated area to produce uplift must come from somewhere, so we would expect a complementary depression outside the zone of uplift.
Yeah, that's a key point.
Yeah. If the whole mantle participated in the relaxation, these downward movements would be fairly widely spread over the Earth's surface, and therefore be of small and probably insignificant magnitude. But if, as we suppose here, the flow is restricted to a narrow asthenospheric shell, then the downwarp will occur in a restricted zone immediately peripheral to the uplift with large and significant displacements.
And I'm just kind of looking at it too, with you just having said that. And I mean, we saw the visualization for a lot earlier on, the Laurentide ice sheet over here on this part of the North American plate, and then the ice sheets over here, over Europe on this part, making up two corners of the Azores. And I mean, I know the crust isn't super thick, especially oceanic crust isn't really usually more than like 10 kilometers thick, or maybe 15, 20 or so. But the you know, the continents can be 100 kilometers thick at their deepest.
Yes.
But still, they clearly are one unit, because we see these plate boundaries, and so it's almost like a seesaw effect. I can visualize, at least, not saying this is the case, but if there is like even just a slight seesaw effect, where this placing pressure down on North America is causing this to tilt up a little bit. And then the same thing over here, because this is the corner of the Eurasian plate, this then tilts up, and then when that goes away, now all of a sudden it would tilt down. And there could be a lot of vertical movement there, if that is even a minor effect. Even though the crust isn't that thick, they are these clear, coherent geologic features that exist. So there's more structural rigidity to them than seemingly meets the eye. Like there's quite a lot of structure there, or else they wouldn't exist in the first place.
Right. Now the study here, let's see, he goes on, he says in Canada, I have a graphic I can share on this too, but in Canada, the total amount of rebound at the center of uplift was probably between 400 and 1,000 meters during the retreat of the ice sheet between 18,000 and 6,000 years before present. So 1,000 meters, that's a pretty significant movement.
It's a huge movement.
Yeah. Now, of course, that played out since the final phase of the deglaciation, and you can look at the elevated shorelines around Hudson Bay, and you'll see very clearly that the earliest ones are much more prominent, and they have a larger space between them, right? Which is showing basically that the uplift was fastest at the beginning of the uplift, and it's been slowing down ever since.
Here's some of those features that you were talking about earlier too.
Yeah, and you saw from the graphic you had that was a solid mass of ice across there.
Do you think we're headed towards another ice age? I mean, we are obviously in the grand scheme, but like some people right now think this interglacial is going to come to an end soon. But we do see, if we talk about just energy, I mean, we're putting a ton of energy into the Earth right now, taking all these sequestered fossil fuels over millions of years, sequestered sunlight, burning that. And then also our sun's doing a lot of things. The sun's the main driver of climate. That's really, really active the past 1,000 years, going all the way back to the medieval warm period. I mean, what's your sense? Do you think that we're due for a cold snap soon, or maybe 500 years from now?
I have. It's a good question, and I got to answer it by saying I have deliberately withheld an opinion on that. Why? Well, I feel like we need to have a better understanding of what caused the last ice age, and we don't really. We don't. I mean, there's ideas out there, and I think some of those ideas are more plausible than others, but somehow, like if we go back to the Eemian, it was warmer. Now we're back to 100. Eemian was typically considered to be the analog for the Holocene, although it's not really. The Eemian lasted about 13,000 years, from 116 to 129,000 years ago, right? It was within the Eemian. The thing that makes it not typical of the Holocene is the fact that within the Eemian there were some very large climatic swings that we don't have their counterpart in the Holocene. But overall, the Eemian was warmer than the Holocene by a pretty fair amount, maybe 2 to 4 degrees warmer. There's evidence now that the Greenland ice sheet shrank to only half of its current size, mass, and melted so much back that it actually separated down to ground level in an east-west transect, roughly across the center, the latitudinal center of Greenland, north to south, and it was actually 2 ice domes. So you could have traveled from what's it called, the Fram Strait, I believe it's called there, to the left of Greenland, right across, right in there, yeah. And sea levels estimated to be, by some estimates, up to 30 feet. Most of them are around 20 feet higher than now. Okay, so where was I going with this? Well, then you had the end of the Eemian, which apparently happened very fast, and the final phase of the late Wisconsin, at least in the Western Hemisphere, in the North American version of the ice sheet. The late Wisconsin establishes the time frame, right, which end of the Eemian to the beginning of the Holocene, the end of the Younger Dryas, would have been the late Wisconsin. So that represents the time span of the last ice period, which differentiates from Laurentide, Cordilleran, Fennoscandian, which is the names of the ice sheets themselves. So that's because the evidence for that last glacial phase was first studied from deposits and sediments in the state of Wisconsin. That's why it's called that. But anyways, within that, which was previously considered to be one essentially unbroken period of deep glacial cold, was now interrupted by periods of considerable warmth and then back to cold again. In fact, there are studies that suggest that Hudson Bay had forests around it roughly 35,000 years ago. Now, if that's the case, the ice sheets must be extremely retracted in size from where they are now. From what we assume they were in late glacial maximum. So glaciologists and paleoclimatologists invented some new terms. So you've got glacial and interglacial. Okay, so glacial would be going back to late glacial maximum. What's behind you right there? That's a glacial age.
Oh, yeah.
Interglacial, that's us now, the Holocene. Well, the climate the oscillations haven't been to those extremes every time. Sometimes the oscillations have been less. So if you have a warming period, but not as warm as the Holocene and not the disappearance of the entire North American ice complex, that's called an interstade or an interstadial. Then if it goes cold and you have a growth of the ice sheet, but it's not fully to what you see here behind you, that's a stadial. So you have full glacial, full interglacial, a stade or a stadial, and an interstadial. So you can picture it almost like this. From this to this. Like this to this.
And that's what that Caribbean sea surface temperature graphic showed. Is to show these longer rhythms that went to really high, really low, but then also those in between periods.
Exactly.
And a question before we get to that, because we're talking about the injection of energy into the system, and a comet impact or some sort of impact is a very fast injection of energy, so that makes sense. And looking at these ice sheets, of course, there's going to be sea surface ice as well. So this isn't showing really the sea surface ice all that well. And of course, we have Antarctica down here.
Yeah.
But ice has a very high albedo. And so it seems to me that when this injection of energy comes in, of course, there's a lot of melting, and then the Earth finds a new stability and equilibrium, in part due to just how light is being absorbed from the sun. And then during the glacial period, because oceans absorb a lot more energy than ice, ice will reflect most of it out, and snow and et cetera.
Right.
And then during the glacial period, there is a much higher albedo effect that keeps it colder. And the interesting thing as well is that these are centered at the poles. So during the solstice, and today it's one day off of the solstice, this is 22nd December, folks, is that you're going to have, for example, during the summer solstice, the northern hemisphere is going to get continuous sunlight. And so if there is a lot of ice there, it's going to have a pretty big albedo effect. And then for right now, for us, it's a winter solstice, northern hemisphere. Right now, it's Antarctica doing that with 24-hour light, but because it has such a high albedo, pumping a lot of that energy out. But it seems to me that a comet coming in is a very easy explanation that's probably happened before, Younger Dryas being an example, of a quick energy injection. But it's like, how does the energy leave to then be significant enough for these giant ice sheets to form again? And I know a lot of people talk about ocean currents, but I just had in my head, like, maybe if we enter into a really long, severe grand solar minimum, that perhaps could do it, because that is the ultimate energy source that's everything is derived from. What are your thoughts on that?
My thoughts are that, I mean, that's how we have to be thinking. I mean, again, remember what we showed last on the episode you did before with me when we showed the influx of comet falling into the sun, a sun-grazing comet, and which has led me to think that, if there is a large influx of, mass from whether it's the Kuiper, wherever it comes from, and that's, I mean, I think that's a model that we could realistically consider, where that rather than randomly, uniformly through time, a comet comes in, breaks up, that we may have episodes where we have multiple comets, in effect, comet storms. And what would the effect be if you had multiple impacts into the sun, or large impacts? What was the object that was so darn large that you were telling me about last time?
UN 271 Bernardelli Bernstein.
Yeah.
140 kilometers across.
Yeah. So what if something even half that size or a quarter that size, or a fragmented object pummeled the sun even over a period of time? Maybe rather than just one event, you have a multiple event. Could that introduce feedbacks into the system, into the stability of the sun? I don't know, because I haven't studied solar physics nearly enough to have any kind of an educated opinion on it. This is just like new. I mean, because I went from, studying the Earth and realizing relying purely on terrestrial triggering mechanisms doesn't seem to provide us with what we need. So we have to think big and start thinking much larger. Well, then that's what led me to think, there's got to be what's happening out there is translating into what's happening down here. We can see the after effects of these changes out here, but what is that exact process of transmission? That's what I'm trying to wrap my head around right now. And you brought that up. Now, if you have, like, say, a very large, we know that from core samples of the ice sheets that there can be layers in there that might be extremely dirty because of large volcanic eruptions, right? So if you have a large volcanic eruption and you have the deposition of fine volcanic ash over the surface of the ice sheet, you're going to change its albedo, obviously. Now, but what does that have to do with the formation? See, I still am at a loss to understand what starts an ice age at the beginning. I think of various scenarios like, well, if you had a multiple, because here's the problem. When you look at that right there, that's the result of a whole lot of precipitation right there, right? Where did all that water come from? Well, it came out of the oceans, right? We know oceans lowered, right? So, but in order to evaporate that much water, I mean, it requires heat to evaporate, right? But now you precipitate it out over land, but there's not enough heat to melt it. And so it just accumulates year after year after year for thousands of years until the doggone thing is a mile and a half, maybe even 2 miles thick. So it doesn't make sense, because it's like simultaneously you have to get a whole lot of water vapor into the atmosphere and precipitate it out in the form of snow. So that requires heat. But then on the other hand, it has to be cold enough that for year after year after year, there's not enough heat to melt. Right now, obviously, we get considerable snowfall over northern U.S. and Canada every year. Come spring, there's enough heat that all melts away. Right? We know where that heat's coming from. It's coming from the sun, and it's coming from the angular tilt of the Earth towards the sun, right? When the northern hemisphere is tilted towards the Earth, it gets more direct sunlight. More heat per square centimeter, and all the snow melts. Ice age, that can't happen. So that's the part that's hard to figure out. How do you do that? How do you accomplish simultaneously enough heat to be drawing that 6 million cubic miles of water out of the ocean, drop it as snowfall over the continents, but it's so cold that the continents, that it doesn't melt? Well, see, that gets us back to the energy paradox again, see? And because I don't know, the question you asked, I would hesitate to attempt to answer it. Once I've got it all figured out, I'll get back to you on it, okay? After I've got this whole thing all figured out. I may have to come back for another lifetime, or figure out a way to extend this one another 40 or 50 years. If I could just have like 30, 40, 50 more years, man, could I get some thinking done, some research, serious research. But anyways, that's where I'm at on that question.
But I mean, who knows? But it's probably not going to happen like the day after tomorrow and 10 years from now. Like, I mean,
No.
These cold snaps do take some time, like geologic time would be fast, would be like 1,000 years, for example.
Well, the climate change, the temperature change can be really fast, but it takes thousands of years to accumulate that glacial ice.
Yeah.
Right. So there's this lag, and the actual temperature change in some cases is almost instantaneous. 3 to 5 years or even less. I mean, as the signal is preserved in some of the sediments, particularly the ice cores. It was the ice cores, the GRIP, the Greenland Ice Sheet Project 2, and what was the other one? The European version. There was two of them that went between 88 and 93, and it was those 5 years of going to the summit. See, the Camp Century and the dye cores that they took, DYE, were near the perimeter of the Greenland ice sheet. And the ice is very dynamic there, whereas it's much more stable at the summit. So, but the summit was really challenging. It took 5 years, to drill to bedrock. But those cores were showing that there were temperature changes of up to 7 to 8 degrees centigrade in less than 3 years, or maybe less. That's how strong and quick that signal is in the ice cores.
So that could be volcanic then. Like if you have a volcanic eruption, let's say in the southern hemisphere, that could pump a lot of water into the atmosphere. And then, I mean, a lot of that ash would go to stratosphere, but it's mostly going to, I'd think, settle out more local So if it's in the southern hemisphere, that ash isn't going to blanket down in the northern hemisphere and reduce the albedo effect maybe as much as it could. But then that water will circulate very rapidly in the hydrosphere, and then that could provide, because again, we talked about how much water's in the mantle.
Yeah.
All these OH bonds, and then as that comes up and depressurizes and mineralogical changes, water precipitates out. So that could be one explanation, or at least part of the puzzle, perhaps.
Yeah, part of the puzzle, because if that was the full answer to the puzzle, you probably deserve some type of a prize. I don't know about the Nobel Prize, but some kind of prize, because that's been an ongoing question for 50 years. Trying to really more than that. And the problem is that in the older days, before radiocarbon dating, it was possible to imagine you had 50,000 years to go into an ice age and another 50,000 years to come out of the ice age. Well, that's where the energy paradox came in, is because, wait a second, that the timing doesn't work anymore. That was essentially the conclusion.
There's information on both sides that the entering and the exiting of ice ages is much more rapid than most people think.
Correct.
Okay.
Absolutely correct, yes. So let's see, John T. Andrews, this is going back to 73 again, John T. Andrews' article that appeared in the Arctic and Alpine Research. This was the title of it. The Wisconsin Laurentide Ice Sheet, Dispersal Centers, Problems of Rates of Retreat and Climatic Implications. So the article begins, isochrone maps. So another maps showing an isochrone would be simply a line of where the ice receded to at a given time. So if you do a chronology of the disappearance of the ice sheet incrementally, and you draw those lines, they're the equivalents of topographic lines on a topographic map, but they're isochrones. So isochrone maps of the late Wisconsin deglaciation of the Laurentide ice sheet enable estimates to be made of changes in the volume and area of the ice sheet. The average marginal recession between 12,000 and 7,000 years before present is estimated at 260 meters per year. So 260 meters, to convert that to feet for people to think in feet, that would be about just over 850 feet. Okay. Now here's the point. Here's the crux of what they realized, is that it varied little between the northwest and southern margins. So look here. So if they're looking at phases of retreat, you go down here behind you, like these lobes down here in the area of Ohio and the Great Lakes, that's the southern margin. The northwest is up there, all the way up, and you can see the northwest is up there, right in there. Yeah. So here was what they realized when they developed these isochrone maps, that the northwest rate of retreat was the same as the southern rate of retreat. Does that make sense? Not really. This paper is mainly concerned with the rates of marginal recession of the Laurentide ice sheet, with particular emphasis on the retreat rates experienced during the deglaciation of the northern United States and southern Canada and the Canadian Arctic between 18,000 and 7,000 years ago. Of primary concern is the energy balance at the margin of the ice sheet required to promote the rapid late Wisconsin retreat. So he just defined the problem right there. He goes on to say the growth and development of the Laurentide ice sheet complex is still an enigma. Unexplained is the growth of the ice cap in its gathering grounds on Baffin Island, Labrador, and Keewatin, where at least today there are low winter accumulation regimes. Equally unexplained is the southward penetration of the ice sheet to latitude 40 degrees north, or so, where even under full glacial climatic conditions, mass loss at the southern margin must have been considerable. At its maximum extent, the Laurentide ice sheet complex was approximately the same size as the present Antarctic ice sheet. In the last few years, the increasing number of radiocarbon-controlled marginal positions led Bryson et al. And Prest to produce isochrone maps on the deglaciation of the Laurentide ice sheet. These maps have been used to estimate the changes in area and volume of the ice sheet as a function of time. The average annual rate, and here we're getting to the crux of the matter, of marginal retreat of the Laurentide ice sheet calculated from the reduction in area was 260 meters per year. Now that's assuming that it was a constant over the whole, through the whole deglaciation phase. This high figure immediately raises the question, what energy sources are available to cause such a rapid retreat? A significant aspect of the Laurentide deglacial history is the high energy inputs required. The paleoclimatological conditions at the southern margin of the Laurentide ice sheet during the late Wisconsin have been discussed by many. A significant aspect of the Laurentide deglacial history is the high energy inputs required, he's reiterating, to produce the apparent rates of marginal retreat. The problem imposed by the estimated rapid rates of retreat is illustrated by figure 7. I can pull that up if you want to see it. If the retreating ice sheet maintained a dynamic flow, the profiles of figure 7 represent an approximation of the marginal form of the ice sheet. Now here's part of the problem. If it's receding rapidly, well, then it's not being fed from the zone of accumulation, presumably. So now you're confronted with, well, okay, so for thousands of years, there has been pretty vigorous accumulation. Otherwise, this whole thing isn't going to grow. Now, all of a sudden, are we assuming that that's stopped? See? Or is it still happening? Is it still accumulating? Well, here's the problem now. See, if it's a static ice mass and you calculate 260 meters each year, but at the same time, if it's in the zone of accumulation, you now have to take the sum of not only its advance, but its retreat in order to calculate the real volume of ice loss. You see what I'm saying?
Yeah.
Yeah. Okay, so a retreat...
Because remember, folks, glaciers are very alive. They move. They've carved the landscape. So they're not... Sometimes we think of just these ice sheets as just sitting there, but they're always flowing. Viscously. Down.
Flowing viscously, yes.
Yeah.
Good point.
A little bit more viscous than honey, but still not completely like metal or something.
Not like not like warm milk, for example.
Yeah.
Okay, so a retreat rate of 200 meters a year thus requires a tremendous vertical mass loss.
But it all seems to be coming together, like based off of where you were 20 years ago, let's say, with studying this. Do you feel like a tremendous amount of progress has been made in understanding this, and that you feel fairly close? Like you said, you want 30 more years to get it figured out.
Yeah.
Like you could see the finish line ahead.
Yes, I do. And one reason is because I began to speculate in my mind an extraterrestrial component. I read these papers that we're looking at here literally in the 70s, right? So I was thinking about this stuff back then. In the late 80s, it was because I was looking at the Carolina Bays and speculating as to an extraterrestrial origin of the Carolina Bays. And, they're right here in my backyard. And I went down, I didn't actually get down, maybe 91, I think I went down and explored some of the Carolina Bays in South Georgia, even hired a pilot to fly me over the bays so I could see them from above. And I went back and I was looking at maps, and you're probably aware of, you've looked at the bays enough to know that the long axis of the ellipse is oriented, so it's pointing to a region sort of up there near Lake Michigan. Okay, and if you follow around from the bays in Carolina around to Georgia, what you see is that orientation shifts. And not only does the eccentricity of the ellipse also changes, it becomes much more circular. So you've got this decrease in eccentricity between the Georgia bays but anyways, I was focusing where the bays were the most dense, and that was roughly right around the borderline between North and South Carolina, and realized, okay, the orientation was roughly 45 degrees west of north. So you had a northwest-southeast orientation that was about 45 degrees. And you had the prominent rims on the southeast side, which would have made sense if you're talking about some kind of an input of force, like a hypervelocity object. And at that time, I'm thinking, okay, if it was an impact produced, I'm thinking more something along the lines of Tunguska. I'm thinking of an aerial burst, which then has a conical shock front leading it, and that is what actually is hitting the ground. And if it's conical, if it hits the ground at an angle, its cross section is going to be an ellipse. And I thought, okay, that makes sense to me that, it could have been a massive, like, fragmented comet. Maybe even a lot of it was chunks of ice, right? So that's how I started thinking about it. And then that would be consistent with the rims being prominent on the southeast, because you can picture if it's coming in this way from the northwest, it's going to push everything to the southeast. So then what I did was I thought, okay, if this is a celestial object coming in from the northwest, and at the time, most of the dating, which was radiocarbon dating, taken from sediments on the bottom of the Carolina Bays, showed that it was late Pleistocene in age. So then I just speculated and said, well, what if it's like, terminal ice age? So if I do the back azimuth of that trajectory, where does it take me? Well, it took me right over the ice sheets. And then that led me to go, okay, well, if there was an influx of fragmented comet coming from the northwest, the Carolina Bays are on the coastal plain where you have unconsolidated soft sediment. As you come up into the Piedmont, now you get rocky sediment, and you can actually see the bays are very prominent in the coastal plain, and then they sort of disappear as you get into the Piedmont uplands, right? And if it happened during late glacial maximum, you now have 30, 40, 50 miles of exposed continental shelf that's now drowned. So in the rising sea level, it would probably erase any rims and infill any depressions. But what it led me to was, okay, is there anything unusual that happened to the ice sheet around that time? And then I remembered something. I remembered that I had read a book in 1980 called The Quest for Atlantis by Cedric Leonard, and he has a chapter in there where he talks about the cataclysm of 10,000 BC, and he mentions the formation of the Channel Scabland, right? Now, he doesn't necessarily tie that in with an Atlantean catastrophe, but he points out that it's roughly in that window. And then I remembered, well, in 1970, right out of high school, me and my buddy drove out there from Minnesota, and we drove around that area of the Scablands and up the Columbia Gorge, and I remember being very, very impressed by the landscape, but not having the slightest clue what the story was or how it came to be. But that's what led me on this quest that ultimately has taken me out to explore the floodlands 25 times or so, almost every square inch of it, right, to try to get a better understanding. So it's interesting. It started kind of with the Carolina Bays. Then it progressed to hypothetically thinking multiple impact event over the ice sheet, right? So in 1995, I gave 5 lectures at Warren Wilson College up in North Carolina, where I basically described almost completely in its present form the Younger Dryas impact event. And I used Tunguska as a model. I talked about the Carolina Bays. I mentioned, how the advances in astronomy and geology, both of which were pointing to a much more vigorous impact rates than we had imagined. That was 95. So by that time, my thinking had consolidated around this idea of potentially the Younger Dryas being triggered by an extraterrestrial impact. So to answer your question in this big roundabout way is that in 2007, when the Firestone paper came out proposing almost the exact model I had described in these lectures, it was very gratifying and exciting to me. Yes, it was.
And that paper came out with new evidence too, because it showed like these more impact, like direct impact
yes,
evidence signatures.
Yes.
Whereas you were looking at the kind of, you could say, broader and less direct, but still obviously influenced, if this is the case, influenced by that, the geology and Carolina Bays and such. So you had like a lower resolution picture that you were still able to visualize it and get it in your mind, and then they came along with the high res data.
Yeah, and they came along with the microscale evidence, basically, is what they were talking about in that first paper. And so I kind of consider that a turning point. Of course, it met with fierce criticism, almost right out of the gate. Within 2 months, 3 months of the publication of that paper, you already had attacks on it, which, the normal time between submission of a paper and actually getting into press is typically 6 months to a year, somewhere in that range, right? Well, here you had, I think the Firestone paper was published in December, and by early March, you already had the rebuttals and so forth. And as I read those rebuttals, I thought, these don't seem to have a lot of substance to them. And I think this is more knee-jerk than anything. Because, you had this fierce opposition to the idea. I think it's gone quiet now because so many independent teams have found that proxy evidence.
It may have gone quiet, but I did a Google search for Younger Dryas impact hypothesis just a few days ago, and those are still the majority of the papers that show up on Google Scholar. So you have to kind of filter through those to find the actual papers by, what was it, like Sweatman and others?
Oh, yeah.
And now more independent groups as well, but it's like all of them are the rebuttals near the top. So there's also like this algorithmic sorting that's occurred.
That's got to be, I think that's got to be intentional. While I've got this up, let me talk about it just a second, and then I'm going to show you something else related to what you just said. But here you look at the profile. So here you have here's your 200-meter recession. But the point that they're talking about is you have to think in terms of the height of the ice sheet itself, because what they're saying is, okay, you can pull it back 200 meters, but that requires an enormous loss of mass of the glacier. And so then they have 300 meters, because this is the range that they've estimated, up to more than 300 meters per year.
Yeah, the volume is dramatically different between 10 and 200 or 10 and 300. It's like insane.
Yes. So this is ice marginal profiles illustrating the vertical mass loss required for retreats of 10 to 300 meters per year. Let's see here. We can rates of ice retreat in meters per year. Let's see, just for the sake of time, and I'm going to have to go shortly. But here we go. If a mass loss, let's go here. If a mass loss of 9 to 45 meters of water is converted into energy required to melt so much ice, then a minimum value of between 72 and 360 kilocalories per square centimeter per year at the southern and northwestern margin. It is necessary to look at these estimates in the light of available energy sources. Net radiation is the primary energy source over most ice surfaces that lead to ice melt, although with an increase in maritime influences, convection and condensation increase in importance. Net radiation is a complex heat source. It is the net product of incoming global and long-wave radiation and outgoing long-wave radiation, and consequently is not an easy parameter to model. In the area of the former southern margins of the Laurentide ice sheet of 12,000 years before present, the present annual net radiation amounts to 40 kilocalories per square centimeter per year, compared to between 5 to 10 kilocalories per year along the former northern margin. So during the Ice Age, the amount of energy you had compared to now, well, look, between 4 and 8 times more energy now than was available back during the Ice Age. So if you put this much energy available at the margins, those margins would start receding, right? These values have to be adjusted for the amount of net radiation falling during the summer months on an ice surface with an albedo of approximately 0.5 for an effective computation of this energy source to ice ablation. And this is showing the isochrone of the recession of the Laurentide ice sheet that was in the paper. And then they basically, that was the problem that was posed. Then the following year, they had a follow-up led by Kenneth Hare, who wrote up the proceedings, and it appeared in the paper, Quaternary Research, Late Pleistocene and Holocene Climate, Some Persistent Problems. A series of lectures as comprehensive as those reported in this issue leaves very little for a general reviewer to say. The lectures have included many of the leading specialists in each of the subfields of paleoclimatology upon whose work a reviewer must lean. Moreover, there has recently been published a fine synthesis of what is known about the overall character of Quaternary and Holocene climates. All I can do in this situation is to point out some disturbing, I like that, and persistent problems that tend to defy solution. And that essentially is the problem. Yeah. It concerns the energy requirements of glacial retreat, a problem clearly set out by Andrews, which is the one we just quoted from. And then we have good evidence as to the retreat of the Laurentide ice limit in North America in the period 14,000 to 7,000 BP. By making reasonable assumptions about the geometry of the remaining ice, we can estimate the energy flux required to bring about the required melting. Even the most conservative estimates exceed the rates of energy delivery that exist today in those areas. Calculations for the Scandinavian ice reveal a similar paradox. In other words, to get rid of that ice, you had to have way more energy than is there right now available.
Yeah. Yeah, if we had a comet or a fragment stream or something fly into the inner solar system, hit Earth, and then also perhaps also some of those hit the sun and create these big solar outbursts, that's only going to add even more energy into the whole equation.
Yes. And I think that's where we have to go, because they weren't thinking in those terms in the 70s, and that's why they had to put it on the shelf and say, we'll get back to this later. But basically, here's the upshot of it, is that this rate of 260 meters per year over the whole retreat phase. Now, we know that wasn't a uniform process. There was short periods in there where that retreat phase would have been very much accelerated, right? Yeah. Assuming that the glacier maintained a dynamic flow, Andrews was able to apply profile theory to estimate the marginal value of the vertical wasting required to maintain the speed of retreat. He obtained values of 9 to 45 meters per year, which requires a heat delivery rate of 72 to 360 kilo-Langleys per year. The lower of these figures corresponds to net radiation values typical of subtropical areas. The higher figure is 3 times as high as the highest known contemporary regional net radiation, which is over tropical oceans. So in other words, take the energy, if it's that higher rate, and I think it's clearly not maybe over the whole retreat phase, but there are times in there where it's probably higher than 360 kilo-Langleys per year. So where do we have the most available heat energy? Tropical oceans. Another study also said equivalency roughly over the Saharan region of Africa. Well, so there we go. Three times the energy, conservatively, I think we could say 3 times the energy that's available in tropical oceans, applied to the ice sheet over the whole retreat phase.
Yeah,
you can begin to see the. Yeah.
And your evidence for it being faster is all the scablands and all the geologic features and water flow erosion across North America.
Yes.
Because you only create that if it's extremely like a crazy deluge.
Yes. hundreds of millions of cubic feet per second
Yeah.
in some of the channels. And I tend to disagree with the current models that these channels were produced sequentially. I think we are going to pinpoint the dating and show that they're almost simultaneously over broad geographic ranges, including even in Europe, that this Fennoscandian was also undergoing catastrophic meltdown. Yeah, I mean, there's definitely evidence of that. And there's evidence of gigantic flows in Siberia, in the Altai mountain region, which would be fun to talk about that, because up until the discovery, with the thawing of the Cold War, we were able to start, American scientists were able to get together with Russian scientists, and that's when they learned that there were mega floods. The Americans are saying these Channel Scabland floods are the biggest floods in the history of the Earth. Well, now the Russians are coming and saying, well, we have evidence of floods that are probably as big, maybe even a little bigger. But luckily, the top paleohydrologists of America and Russia got together and teamed up and said, hey, this is obviously a global phenomenon that we're looking at here. Yeah, and I think really what both of us are interested in is how do we link, because I'm convinced now that we have to go outside the bigger picture to explain what we've seen down here below. I'm 100% convinced of that. And that was the roadblock that all of the earlier thinkers, they were pretty much focused on purely terrestrial-based triggering mechanisms. And that's why they kind of gave up in frustration. But like you just said, it could be the sun, it could be a whole combination of things. And that's where I think both of us in our thinking are heading towards this idea of a more holistic model of phenomena, terrestrial and celestial, and the interactions of the two.
Yeah, it's just interesting because so many people, they look at the formation of the solar system like it's just gravity. Then there's some people that's like, it's just electromagnetism. It's like both of them are active, folks. Like, we can look at both of these, and gravity has certain use cases and electromagnetism has other use cases. I guess the final question, if you have the time, if it's something that you can quickly share, if you don't, that's not a problem. You can reschedule or leave it lingering in the ether. But I wonder if you've had any dreams or kind of almost spiritual events that have given you insight into this. I've had some interesting dreams before about Earth events and more that I've shared on my channel. But I find that what you're researching into all the time, it's filling up your psyche, your subconscious, and sometimes you're also giving clues. Like Einstein had a dream about relativity, I guess, and tons of examples of this. Have you had any that you can point to that you recall off the top of your head?
Sort of, yeah. I've told this story. And 1969, I just out of high school and living in rural Minnesota near Minneapolis. And the Minnesota River discharges from a point. If you look at a map of Minnesota, you'll see that there's this unusual bump on the western boundary with the Dakotas. And even as a kid, I used to wonder, why is that bump there? Why didn't they just draw a straight line? Well, years later, I learned why, but right there, by that bump is the headwaters of the Minnesota River. And it flows into the Mississippi right there by St. Paul, Minnesota. Yeah, there's the bump.
Okay.
Now you'll notice there are these elongated lakes. And one of them, if you come down, you'll see it's big, called right there just below the bottom of the screen. If you pan up a little bit, it'll be Big Stone Lake, where I just saw. There it is, Big Stone Lake. Come down over that elongated lake, down lower right. There it is. Come down. Okay. There you go. Big Stone Lake. Why do you suppose it's called Big Stone? Well,
probably big stones there.
There's a bunch of big stones there, right? And those big stones are the result of the catastrophic outburst of Lake Agassiz, which was just to the north of here. Lake Agassiz was this gigantic meltwater lake that covered huge regions. It was as big as basically all the Great Lakes put together. And it had three main outlets. Now, the southernmost outlet was this one, which led into the Mississippi. So all the water draining through here went to the Mississippi and was ultimately conveyed to the Gulf of Mexico. And you can follow that. If you zoom back in, you're going to see an example, a beautiful example of an underfit river. So go back to, let's see. Okay, go back to terrain view. Yeah, okay, so now the river, the Minnesota, that's not the Minnesota River. It's dammed up, so that's a lake. But if you follow that channel down current, you're going to see when it gets, there we go. There's the Minnesota River compared to the channel it is flowing in. The modern Minnesota River did not create that channel. That channel was created by a gigantic glacial outburst flood. Okay? And you can follow that channel all the way down. It gets a little obscure in some places, but then you'll pick it up again. You can follow that all the way to its confluence with the Mississippi, all the way over there by St. Paul. So let's see. And once you zoom in, you can start beginning to see some of the really interesting flow features, things that would have been islands. Now, this was named Glacial River Warren, and the peak flow rate of Glacial River Warren is estimated to have been about 4,000 times greater than the flow of the modern Minnesota. Now there, you can see the underfit. Let's see, we've got two streams flowing together there, see?
Yeah, quite a nice look there. This terrain map is terrible, but regardless, you can kind of see it.
But you can see it, yeah. So, but yeah, LiDAR shows this up very nice. But yeah, you can pretty much see this is what's called an underfit river. The river is disproportionate in size to the channel in which it's flowing.
And now, the height of these cliffs too, because these cliffs are what, like at least 200-300 feet high?
Yeah, in that, yeah. The area that I was in near Minneapolis, they were between 200 and 300 feet. The bluffs.
I don't know the contour interval here. It just says 1,000 feet for the total elevation.
Yeah, we could easily, by switching over to Google Earth, we could easily figure that out. But if you zoom out, and then you'll see that the thing winds around in it, and then it loops to the north. You'll see down there somewhere right in about there. Yeah, at Mankato, it loops and goes north. See that?
Yeah.
And I'm guessing it probably ran into a wall of glacial deposited moraine. Okay, so now we're getting to my old stomping ground.
Here's
and you
the
can
Mississippi.
Yep, so you see the confluence of the two right there by Hastings. Right there, you see the two rivers coming together. Right there, yep. Now, at the flow, the channel of the Minnesota is much bigger than the channel of the Mississippi, but the current flow discharge rate of the Mississippi is greater than the flow of the modern Minnesota. Now, let's go west of there, and I'm going to show you where I had this epiphany. Okay, so back in the summer of 1969, and I don't think the airport was as extensive it was now, but somewhere up on that flat area, above the bluff, every weekend they would have free rock concerts. They would set up a stage and they would have free rock concerts. And I liked it because it was free and it was really a cool area. So one rock, I don't remember who was playing, probably some local band. You can see that there is this gully that comes in. You over there see right there, yeah, where that gully comes in. I strolled, it was like a break in the music or something, and I strolled over by the airport and stood on this knoll right up on top of the bluff, go up on top of the bluff, right in there. Yeah, I was up on top of the bluff and I was looking out over the chasm here, and I was looking down at the river, and I could see that the river had entrenched into the alluvial bottom of the floodplain, right? And as I stood there, I looked across, and I could see a pair of bluffs on the opposite side. And if you zoom out, You can see them. You can zoom in, and you'll see that there is a set of, they're not quite as high, but there's a set of bluffs. Yeah, there it is. You can see it very clearly down there next to the highway. Okay, so looking over this, and there you can see the bluff is not as prominent, but you can see it from the ground. There it is, right there. So I had this kind of like this sudden sort of very strong intuitive sense that I was looking out over the basically the channel of a giant river. And of course, I knew nothing about it, and they hadn't taught it. A lot of the people, well, I learned about that in school when I was in second grade. Well, maybe, but you probably didn't realize it was Glacial River Warren. It had a peak discharge 4,000 times that of the modern Minnesota River, that it was discharged from an outburst flood caused by, Lake Agassiz, et cetera, et cetera. But anyways, that was for me a very important milestone, was having this sense that looking into that valley, that it was like a giant river valley. And then I forgot about it for 10 years. It was 1969. And then in the late 70s, I had read several books. I had read Velikovsky's Earth in Upheaval, which I still recommend. Now, Velikovsky, when he strayed into astrophysics, he went way off. But his first book, Earth in Upheaval, is an interesting compilation of the geological evidence for catastrophe integrated with mythics. So he gathered all of the available geological information that was available in the 50s and what was available through the work of ethnographers and mythologists and so forth. And that book integrated that. Well, then his next one, it was what was it? Ages in Chaos, I believe, where he tried to explain the trigger, or explain the cause of these catastrophes and the origins of these myths, and that's where he kind of went crazy, I think. It's talking about Venus and Mars being discharged out of, I guess what it was, the great eye of Jupiter that you see right behind you there.
Oh.
Right. So but he had no basis. He had no basis in astronomy or astrophysics. So if people ask me about him, I say, well, I think it's a valuable read. That first one where he's documenting, he's compiled myths, he's compiled geological evidence. But if you go to the next book, he's going to try to explain, and that's where I think he goes off base. But the first book is a good read. So I had read that. And then in 1978, I came across a hard copy of Charles Hapgood's book, Path of the Pole. And I just met somebody who was writing a book and using that as a reference. And I thought, boy, I'd like to get a copy of that book. And then not too long later, I was in one of these library tent book sales. And there on the table, Path of the Pole by Charles Hapgood for $2, hard copy. So I snatched it. It's still back here on my shelf. But I worked my way methodically through that book. I went through the reference section, which was 300, 400 references in there. And I set out a goal. I was going to track down as many of those references as I could. So I spent probably up to 2 years going to a local science library, in a science center here, that was set up for public to do science research, and nobody ever used it hardly. And I went in there and started doing research, and the librarian got interested in what I was doing, researching. So did one of the astronomers there at the center. Anyways, the upshot of that was over the next couple of years, this is pre-internet, of course, but the Fernbank Library was then integrated into the interlibrary loan system, so over the next couple of years, I got dozens and dozens of papers sent in from universities from all over that had been referenced in Hapgood's book. So I was studying and reading those diligently, by the 80s. So yeah, definitely a major, like I said, gratifying moment for me was when I saw the Firestone paper. And all this thinking I had been doing for 15 years or longer going in that direction seemed like, okay, I wasn't just there's others, top scientists here that have, Jim Kennett. I mean, my God, the guy's got, 400 papers going back to the 70s. He's one of the leading researchers on the Younger Dryas. And interesting when you read some of the popular accounts attacking or supposedly refuting the impact hypothesis, you say, well, okay, so and they almost paint this picture of these fringe scientists came up with this theory, but the experts have dispelled that. And in my series on the Younger Dryas, I'm going to completely deconstruct that whole thing that came down.
Because your series is even like a history in some aspects, the history of our understanding of the Younger Dryas, in addition to what we believe it is.
Right. I'm starting with that because a lot of interesting questions and lines of research were raised before the impact hypothesis got proposed. So I'm going back into all of that, and for me, it's a great exercise because it's requiring me to actually go deeper into detail in some of these, and reading a lot of papers that I had only skimmed before. Now I'm really taking them apart line by line.
But no recent major epiphanies or vivid dreams of something happening. Like the one you shared is the big one, definitely one of the most impactful in your life.
Well, yeah, maybe, I cite that one from 69 because it really was almost like I was having a vision. It's almost like I went into an altered state and I looked out at this and had this overpowering sense that the grandeur of this valley was actually a big river. So it was kind of a spiritual. But recently, I'd have to think about that. Not something that's so prominent that I have been having some strange dreams lately, but the dreams I've been having lately have been going back and revisiting places of my childhood, but then they're that place of my childhood, but then they're very different. This is here, and then, this is completely different now, or something like that. So in the last few months, I've had a number of dreams like that, but I haven't really had, let's see, I'm probably, as soon as we...
Wait, and you say this was 1969 that you had this experience?
Yes.
That's exactly when we had effectively a triple conjunction between Pluto and Uranus, but also Jupiter as well.
Oh.
So Jupiter came in, and those are seen. A book you may want to read is Cosmos and Psyche by Richat Structure. If you haven't read that book yet,
no, I have not.
That would be a good one for you to get your hands on. I think you'll really like that. A lot of history lining up with just simply the conjunction cycles, the oppositions, and the squares of the main outer planets.
So given the orbital periods of those, and Jupiter, of course, is much quicker, at slightly less than 12 years, though, the conjunction must have been relatively long-lasting, I'm guessing. What is the angular degree within a conjunction? Is it 3 degrees or 2 degrees each side of the...
Well, so Tarnas talks about these outer cycles as having a really good range of effect of 15.
At 15?
Wow.
Yeah,
and then at 20, it gets it starts to really kind of fade at 20. But even then, if you're a good researcher, you can find the effects. But of course, when it's 2-3 degrees, 0 degrees, that's when it's the most powerful.
Okay.
And 69, when we had the landing on the moon, this is when we have some of the most powerful close alignments, and that's the Pluto-Uranus cycle is 111 to 143. It oscillates, so it's a very long cycle between conjunctions. Of course, oppositions are about half, squares. So it's interesting that you had that experience lining up with that, and it set you on the path. It's like the universe is okay, we need this guy to do this work.
Yeah.
So we're going to give him that experience and give him a tap into the past so he can actually see this happening, because this maybe is a ancestral archetypal memory stored in the earth that then you were just given the vision of. That's what it seems like to me. That's kind of my...
Well, yeah, I'm wondering, okay, and I'm guessing I don't know the date, but it was almost certainly like earlier summer. It was a beautiful day, beautiful weather, and I went back there about 5 or 6 years ago to that very spot. But what I realized was that as I was looking now, it wasn't nearly as obvious because apparently the valley had been clear cut at some point previous to 1969 and had not grown back yet. Because now when I was staying in the bluff, I looked down, I could barely see the river because it was completely overgrown with trees. So it was also the fact that it was that specific time. If I had been standing there and looking into the valley as it looks now, I may have not had that same sensation. But and then the following summer, 1970, is when me and a buddy of mine drove out to Washington and Idaho and Montana, and we drove up through the Columbia Gorge, and I had this sense that I would say it was like, again, it was sort of almost like an out-of-a-body experience, kind of, as we're going through there. You know the story of Gulliver's Travels, right? He goes to one land, it's the Lilliputians, and he's a big giant. And then he leaves there and he goes to Brobdingnag, the land of the giants, and he's little. And everything is big, huge on this huge, right, when he's in that land. That's how I felt, like I was going through this land where everything was so huge and outsized, right? And that was very convincing to me that something happened here, something really extraordinary happened here. And then, I kind of forgot about it. I was following a different path. My interest in geology hadn't become an obsession yet. But that summer, traveling through the West, and that week or so that we traveled up through the Columbia Gorge and then backtracked across the Scablands and Idaho, definitely triggered there's a story here. But at the time, I didn't even imagine that it was a story like whatever happened and created this landscape in the Columbia Gorge. I'll never know what that is. It's too beyond me. So I kind of forgot about it. But now I've been through the gorge, 6, 7, 8 times, and now I look at it and I understand what I'm seeing and how those forces were created, how those forms on a mega scale were created. But that event of that summer of 70, going through that gorge, really made a big impression on me. So even though I didn't really begin to pursue the study of the subject of geology till I would say it's with Hapgood's book, 78, 79, is when I really got very interested in and wanted to know what this story was and that it was being overlooked other than in the fringe material, and Hapgood was considered fringe. Certainly Velikovsky was.
Yeah. Well, just to add some context before we sign off for you personally to think about more, and for the viewers to also contemplate on, Jupiter and Uranus were conjunct in the sky, a once every 14-year event associated with these radical breakthroughs and paradigm shifts, scientific, spiritual, otherwise, in early July. So like mid-July, they were exactly conjunct, like July 21st of 69, July 20th, right around that time frame. And Pluto was just 8 degrees away in the sky. So you have that longer cycle. And then also Neptune was in a 60-degree arrangement with Pluto and therefore Uranus and Jupiter. So all of them were in a perfect geometric alignment. But you have the Jupiter-Uranus cycle at climaxing along against the broader Pluto-Uranus cycle that goes from the early 60s to 73 or so, if you break that 15-degree range. So it's wild that you have that story that radically changed your life path in the long run exactly when that happened, and that is the archetypal signification for those sort of events.
And so, I, of course, had absolutely no idea. I've never gone back, looked at an ephemeris to figure out what was happening early summer 1969. But that's interesting. That's
That was
very
always happy in the
interesting
sky.
because that
Yeah.
was that summer was a major pivotal period in my life for sure. I mean, I just got out of high school. It was the peak of everything that was going on culturally. I got swept into all of that, and then of course I did my own share of experimentation with things. I ended up, going through the whole psychedelic era for a couple of years, and then wanted to go beyond that, and sort of like the universe provided. Again, I learned about this Brahmin priest who was a Sanskrit professor at the University of Minnesota. And I was very interested in now the bigger spiritual picture of things. And, like a lot of people of my generation, we sort of rediscovered the Eastern traditions, right? So I turned to the East. I read the Vedanta, I read the Mahabharata, I absorbed into the Vedas, etc. I studied the Upanishads, I studied all of that. And then while I was studying that, I learned about this Brahmin priest who was also a Sanskrit professor, and he was offering classes. So I went and took classes in Sanskrit, and of course I've forgotten it all, but so I got directly from him some of the interpretations of a Vedantic scholar. And he also taught a type of meditation that had gone back through this lineage of Himalayan yoga masters. So through him, I then encountered his yoga master, who was a Swami from the Himalayas and was part of this whole Shankaracharya tradition, and then ended up studying with him, doing these meditation exercises for the next couple of years. Moved to rural Minnesota, northern Minnesota, with my dad and family, and we bought wooded land, and I basically camped out and lived on that wooded land, and we're building a house on the property, but I was basically living in a tent, and I would go through these meditation exercises every day. And at the end of this, we had this retreat in northern Minnesota, and it was being led by the Swami. And on the final day, now this is after I've been doing these exercises for 2 years, I was at the point where, I would sit out in the woods sometimes for 2 hours at a time meditating, right? Well, then on the last day of the retreat, the Swami did something to me that gave me a mild experience of superconsciousness. And that has profoundly affected my perceptions of reality ever since. I had a really authentic, powerful experience that pretty much left me unable to speak and unable to eat for 4, 5, 6 hours, something like that, because I was out of my senses. And I know he triggered it because we had just had a lecture, and in this big tent set up in a meadow out this is now in the woods of northern Minnesota, and I was sitting up front, wrapped into what he was saying, and then the lecture was over. People are getting up to go out, and he walks by me, and he does this. He walks by me and he goes, on my head, right? Just does this on my head. And I thought it was just like, a sign of affection or whatever. So I walk outside, and we're breaking for lunch, and there's a fairly large hill. And I thought, well, lunch isn't ready yet. I think I'm going to go up on top of that hill. Well, as I'm walking up the hill, I start having this experience. And I get to the top of the hill, and I had this experience of the total unity of everything, of the grass in the meadow, the trees, the people, the clouds, the sky, the sun breaking through, that it was all it was a unified system, and it was sentient, it was intelligent. That was like the experience I had. And I cannot describe it. I can't describe it. It's very frustrating to even try to describe it. But I would say that's right up there with one of the peak experiences of my life. And I really sincerely believe that the Swami did trigger that by rubbing me on my head, and maybe, it was the 2 years of I was doing yoga asanas, I was doing the breathing, I was doing the meditation, and I think that had sort of primed me for this. And boom, I mean, he did that. I, walked out, and as I'm going up the hill, by the time I get to the top of the hill, I look around, and it was like all of everything just sort of fused into this one magnificent, magisterial reality of self-awareness. And I felt like I was a part of it. And I could see the Swami down in the meadow, and he came walking across the meadow, and there was about 20 kids at this retreat. And they're all around him, gathered around him, laughing and giggling and hanging onto his robes, right? It was like their attention was totally focused on him. And I won't even go into what happened after that, because I still don't know if it was a hallucination or it was real. But I had experienced that all of everything, the grass, the trees, the clouds looked like they turned into actually a rotary system, and the shafts of light came down, and I'm sitting on this hill, and I could see the shaft of light coming down, just illuminating this meadow. And it was like so mind-blowing. I'm like, am I witnessing this, or am I imagining this? And I still to this day don't really know. But that was, I would say, was the most profound spiritual experience of this round of incarnation, if you want to put it that way.
I'm very glad you shared that, because that's incredible. And I know everyone watching is going to be is happy to have heard that story, because it's inspiring. And I am very interested in inspiring others right now, or doing inspirational things. I think that is the energy that we are moving to, or at least we need to move to more and more.
Yep.
So unless you have anything else that you'd like to discuss, I would like to.
Oh, there's all kinds of things I'd love to discuss, but unfortunately, I have to go. We've been going 2 hours and 49 minutes.
It's a long podcast.
You know what they say, time flies when you're having fun, right?
Yep.
I don't know about you, but I'm having fun.
Yeah,
and it's great. I want to say this, Stefan. It's great because I get in conversations all the time, and it's always particularly gratifying for me when I'm having a conversation where the person I'm talking to actually understands and gets what I'm saying. So thank you for that. And has interesting things to say back that, okay, now I can take away and think about, because, hey, I don't have it all figured out yet. Maybe by the next time we do a podcast together, hopefully I will have it all figured out, but probably not.
Unless Three Eye Atlas gives us that paradigm shift, and we have that new out-of-body experience.
Yeah, right.
But yeah, I think it's great. I hope that we do more conversations like this. I already saw some comments on your video saying, like, you guys should do a monthly feature. And then the person put in parentheses, or even more often. I was like,
really?
Don't get ahead of yourself, but we'll see. So I want to give you my thanks, and everyone. Randall Carlson's new docu-series, I guess you could call it, on the Younger Dryas is out, and more episodes will be coming. So I'll put some links to all of his work, his channel, all this stuff in the video description. It's all there. And want to give all of you my thanks for watching. And Randall, thanks again for jumping on. And
my pleasure, Stefan. Enjoyed every second of it.
Excellent. Thank you so much.
Next time.